Okay, so tangent lines. We see them in constructions. A tangent line is simply a line that intersects a curve at one point. For our purposes, it's going to be a circle. So really a more broad definition would be it intersects any curve. So it could just be like this. Because when you get to calculus, you'll do a lot with tangent lines. So, tangent to a circle is a line pointing up the circle. It intersects the circle in exactly one point. So there's tangent line, and then we call that point the point of tangency. Okay, now I'm really just going to discuss a couple theorems. Three main theorems about these. They should sound familiar because of our work in constructions. So the first one was the one about radius and a right angle made the tangent line when we were constructing a tangent line. And so here's the actual theorem. That's the Greek. If a line is tangent to a circle, then the line is perpendicular. Well, we can say lines intersect to make right angles. The line is perpendicular to the radius at the point of tangency. So basically, right angle plus a radius equals a tangent line. So if you can do a right angle, any of those two, like so if you want a tangent line and you have a right angle, or you have a radius, then it would make a right angle. And so I'm just going to do two examples of this. So for the first one, what is the value of x? Well, you should say, okay. Actually, I should first tell you this. They in general will tell you, all right, LM and NM are tangents. All right. For this question, I'm going to say, let's assume, I should have had it in there, but they'll say something like LM and NM are tangent lines. After they'll tell you that. You can probably tell that it looks like it's intersecting at one point, but they should mention that. Then we have a radius here and a radius here, and so radius plus a tangent makes right angles. Okay, and now what's formed is a quadrilateral, and the sum of those angles is 360. Triangle 180, quadrilateral 360. And so I can subtract two 90s, and it's 117. And so let's see, one of these, 63. So that one, so basically there's two types of these. One, they could ask you to solve for an angle, which we just did, or they might ask you to solve for a side length, and that's the next one. Any thoughts on that one? I guess let's solve for a side. In the circle, find the value of r this time. R representing the radius. And again, I would have said something like, hey, this is a tangent line. Or sometimes the question will say, assume lines that appear tangent are tangent. So there's a tangent, here's a radius from the center, and so it's a right angle. Okay, and now I have a triangle. That's a right triangle. And we should think back to our thing with right triangles. Well, we don't know it's 30, 60, 90. And we don't have enough to actually, we don't have two lengths of the full sides of the triangle. So we use two Pythagorean theorem. Yeah. So we got r squared, a squared plus b squared, r squared plus the 15 squared. And then the c value, notice that this is the radius and this length here is 9. So our c value is r plus 9 or 9 plus r. Yeah. Sometimes students there want to say r times 9. Okay, so if we solve this, if we work it out, we're going to get r. So really, the only thing I can do to start is the right side. The left side, well, okay, I'm sorry. I could do 15 squared. It's 225. Okay, but the right side, be careful here. Common error is students write r squared plus 81. Okay, but you can't do that. You can't square across an addition sign. You can't just square. If it was r times 9, you could square and just get r squared times 81. Okay, but you can't square across addition. So what do I need to do? You forget what it's called. Back to unit, well actually this is last year in summer assignment. FOIL is what I heard, yes. So you have to write it twice and then FOIL. Thank you. You're welcome.
I recall. This was the unit that I remember everything.
Yeah, what? Let's see, so yes, first r times r is r squared. Outside is 9r. R times 9. Inside, 9 times r is 9r. And last is 9 times 9. 81.
So it could just be 18 hours.
Yeah, right. That's really, I guess, the next step is just. The next step, yeah, would just be to combine the middle terms. Or you might have been taught to do that for like all in one step. So 9r, 9r is 18r. Okay.
Oh, and then it's just a problem for R.
And now it's just solving for r. Yeah, now normally we'd like, there's an x squared and we get everything to one side, unfactored. However, in this one, yeah, like there's an r squared on both sides, and so it just cancels out. Because the next step would be subtracting r squared, and it's gone. So we won't, there will be no factoring on this one because of that. So actually now it just becomes a two-step linear equation with the r. Let's see, so I'm going to subtract 81. And 144 equals 18r. And divide by 18. 62. 8, right? Is that right? But 18 times 10 would be 180, and I subtracted 2 of those. There's 2 times 18 is 36. I wanted to tell you. Now, I think that's it, right? Find the value of r. Oh, and by the way, I want to show you on this one. It becomes r8 here. This would be 17. Again, not the most common Pythagorean triple, but 8, 15, 17. I think we saw it yesterday. So, just so you know, it does become one of those.
Oh, we saw the one with 18.
It doesn't always become a Pythagorean triple. Because it could be decimal values. Okay, any thoughts on page, what was that, 4 before moving on? So we saw finding that property, which we kind of already knew from constructions, but finding an angle and then finding a side as well. Okay, let's flip it over. The next theorem is kind of the reverse, or it is the converse of the last one. The last one said here's a tangent, and then use that to solve for side. This one is there a tangent line? So if a line in a plane, 2D, 2 dimensions, of a circle, it is tangent to a radius, is perpendicular. Is perpendicular to a radius at its endpoint, then the line is tangent to the circle. So basically, if this is a radius and if this is a right angle, then we know that there is a tangent line. So for this question, it would not say assume lines are tangent. No, you're trying to decide is it tangent. So I need to see if this is is segment ML tangent. Is it a tangent line? It will be if this is a right angle, because I have a radius there. And that will be a right angle if this is a right triangle. And I can check if it's a right triangle by putting it in the Pythagorean theorem. Okay, so it's a question mark here. I don't know that they're equal yet.
But you have to write a question mark there.
Technically, yeah. I wouldn't count off if you didn't.
Why'd you put 24 in
No, it's not
parentheses?
like that.
Why'd you put 24 in parentheses?
So it doesn't look like 4 squared, like that. I wrote those further apart, but it's really like 7 squared too. So let's work, and yeah, have you ever seen this before with question mark?
No.
Yeah, if you look textbook online, you'll see the question mark there. Because you don't know that they're equal yet. They might not be. 49, let's see, 24 squared. Somebody help me out.
Yep, I have 576.
625. And then, oh, question mark. We don't know if they're equal. I think they are, right?
Yes.
20, yeah. That'd be 625. Now it becomes a check mark.
Oh, you gotta change it?
I really did that.
You put a check mark. Yeah, because you verified now it is equal. If you don't put these, it's alright. Okay, so that's the converse of the last theorem. They're just reverse.
Cool, I can do that.
Yeah, is it tangent? Well, it has to be a right angle. It has to be a right triangle. If it works in the Pythagorean theorem, then it's a right triangle and a right angle.
So the other radius of the 25 not matter.
Oh, I should have said this
that's
too.
what says prove.
I'll be more clear if I ask a question like this on a quiz or test. I should have said something like NM is 25. It kind of looks, thank you. It kind of looks here like they were saying this was 25. And then we would have to do this as 7. And then it would have been 7 squared plus 24 squared equals 32 squared. Yeah, I'm sorry, I meant to say that whole length is 25, is the 25. Okay, one more theorem. Yeah, this is a good one here. Yeah, let's move on to this one. Last theorem, if two tangent segments come from a same exterior point, then the two segments are congruent. So here's an exterior point. If I have two tangent lines coming from that, the red lines A, B, and CB, and they're both tangent, the red lines, they're both tangent, then they are congruent. Yeah, you can think of this as the party hat one.
Wait, no.
Oh my
If
God.
you draw another dot right there, it'd be like a surprise. Because of the party hat.
Where?
No, like on the first one.
Oh,
Draw like another dot as a.
There.
No.
Oh, yeah, that's the wrong direction. Okay, well.
That would have been like surprise person.
Yeah, that would have been cool.
Oh,
So, yeah, let's prove this one. This is a good one to prove. I'm going to do a 2-column proof. So this is good, cycle in things we've done from the past.
You're making me think about last year, and I try to avoid that.
Oh my.
Maybe watch these and why do you only? Okay, never mind. You usually just write statement and leave them, and that makes me upset because there's multiple ones.
So I didn't give you all the here's what's given, here's what to prove. So let me write it in now. What's provided is circle O with 2 tangent lines. So with tangents A, B, and C.
Why would you name the circle O?
It's circle O, the center point. Is that what you're
Like,
saying?
why would you do that if you know what the sign for circle is?
Oh, with the symbol?
Yeah.
Oh. So here's what I'm going to do. These are already marked on here, I think, as congruent. So I'm just going to redraw this. I would encourage you to as well. Just because I already have them marked as congruent, and they're not congruent. So when I do this work, I just want to make sure we know that they're not actually congruent yet. That's what we're showing. So really the prove, given would be this, prove would be AB is congruent to CB. Okay, so that's what we're proving. Continue. All right, well, we're going to combine, I'll give you the other theorems first, because now we're going to combine what we did in the last theorem with some things from our past. So are you good that there's a radius I can draw on? I can draw on it anywhere if I choose that. And there's another radius I can draw on? Because we just learned a radius and a tangent is going to make a right angle. So that's going to be helpful. Now, right now, that helps, but we still would have like a quadrilateral. This looks like example 1 on the last page. So we have a quadrilateral. Yeah, it does. Any thoughts on what I can do? I'm going to draw on another line. Yes, I'm going to draw on this line to make two triangles. And then if the triangles are congruent, wouldn't AB and CB then be congruent?
I already know it always comes like that.
It often does, right? Like the quadrilaterals, most were triangles. I think that there's another one, but circles. There's not this one. There's another one that comes back to triangles too. So I'm going to draw on that line as well, and now I'm just going to show the triangles are congruent.
Well, you know that O and CB are like the length, right?
Which angle?
ABO and CBO?
That's these angles.
Yeah, right? Because bisector.
Well, we don't know that. We just drew it in. We didn't have anything that we know it's bisect.
Because the radius and the tangent says a 90, right?
So that's what we can do. Yeah, let's go ahead and say we know that's the property from the last theorem.
But we don't know if it's the same thing, so. What? I didn't say that.
No,
Oh,
these are
never mind.
tangents.
We know it's
Yeah.
a tangent, we just don't know if they're congruent.
Right. We know it's tangent. We don't know if they're congruent. So let's say angle
Okay, but like that's not right.
OAB and angle OCB are right angles. That's right. This is a good review. So we first say they're right angles, then we'll say they're congruent. They are right angles. All right angles are congruent, yeah. So now the reason for this is the last theorem. So I'm just writing the last, well, that's not the first theorem. I'm writing this. A tangent at a radius is perpendicular. I just kind of shortened it. Tangent at radius, you can write the full theorem if you want. Tangent at radius is perpendicular. And then I need to say the angles are congruent. It's kind of a two-step thing. So first the right angles, and then angle OAB is congruent to angle OCB. All right angles are congruent. Angles are congruent. Okay. One pair of angles congruent. That's really all the angles we're going to need. Do we see some other sides congruent? These are both radii. We have seen this once in the past. AO congruent to CO. They're radii. Any radii you can draw for the same circle, that is. All radii for the same circle are congruent. That's the reason. I like over here, all right angles are congruent. From the last one, all radii are congruent. This assumes radii from the same circle.
Yeah, it's too loud. It was in the packet yesterday.
No, radii, because it was radius. You cancel that out, put an I in.
No.
Look at this.
This is not. It just looks like radar.
I'm serious. This. It looks like a smiley face. Okay, and finally, what's the last segment? We have two things, we have one more.
The
most
middle.
one.
Shared side.
That's the one that I was thinking of. I just said it wrong.
Oh, yeah?
Then this is side A.
OB congruent to OB.
But then are we gonna
Wait,
use, are we
shouldn't it
gonna
be
use
OB is congruent to BO?
Oh no.
You
Oh my
flipped.
gosh.
No.
Oh.
We're back.
No, the triangles are just next to each other. They're just sitting next to each other, so it's not turned.
But it's a quadrilateral. But you told me that you always flip it. You do.
I can't believe we're back at this. OB congruent to OB. Let's go with that.
Wait, so
Yes,
this one
it is
I
not
never
confusing.
flip them? Wait, so when we do circles, you never flip them?
No, I don't think that's true. So now we have two sides and an excluded angle, which we can't use. However, they're right triangles, and we have legs and hypoteni congruent between the triangles. And so HL will show the triangles are congruent. So the triangle OAB congruent to triangle OCD.
Did you just say something like that?
What?
And the goal was to show the sides are congruent, AB and CB. And so now I'll say AB is congruent to CB because CP, CTC. See, that's a great review of things we haven't done in a while. Yeah. Okay, one last thing I need to talk about, and then we'll be done. What can I answer to help out on that proof? Broke it up into triangles, drew that.
You told me just why.
No, just why.
Why?
Why do I need?
Give me the. That is inaccurate.
It would be more fun. That is a subjective
Okay.
opinion.
Let's finish it up. So the last thing is, again, kind of a throwback to constructions, because we did it a little bit. I don't think we talked fully about these words, though. I think I talked about draw the in circle. I put and draw, like, circumscribe a circle. You just put the circle on the outside. So really, here's the full terms, is an inscribed figure is a figure inside another that touches, like tangents. Like that line is a tangent there, and this line is a tangent there, and at this point, tangent there. So a polygon is inscribed in a circle if each of its vertices lie on the circle. Or in this case, the circle is inscribed in the polygon. So it could be either direction there. Circle inside or circle outside. So we know the opposite like this. So if it was, what have we done? I think it was that triangle, right? And then we circumscribed. So inscribed is the figure on the inside. Circumscribed is putting the figure on the outside. So a circle, this is circumscribed around the triangle. Okay, so inscribed inside, circumscribed around the outside. So I said the triangle is circumscribed about the circle, and the circle is inscribed in the triangle. All right, so last one I want to do here after doing those terms is find the perimeter of this triangle. And we're using the property from the last theorem that we proved. So since these are both tangent, and they're congruent, and so they're both tangent. And since these are both tangent,
Hi, Mr. Hunt.
hi Gussie. And then these are both 15. And finally, since these are both tangent, they're congruent, and so they're both 8.
That is not equal to
So 16,
that should not be.
30, and 20, so 66. What's that?
Why is that 8? Because it doesn't match with 10.
3.
Like where it's 8? Like it's way too short to be 8.
Oh, I mean, figure does look smaller, yeah.
On the scale.
It does look a lot smaller. I don't know.
Yeah. Make sure to write your units.